7 months. That's how long it takes to get to Mars using conventional chemical rockets. 7 months of radiation exposure, bone loss, muscle atrophy, and psychological stress. 7 months where every day increases your cancer risk, where your body deteriorates, where a medical emergency could be fatal because you're millions of miles from help. But what if it only took 45 days? NASA and DARPA were building a nuclear-powered rocket that could cut Mars travel time by more than 80%. The technology worked, the contracts were signed, companies were building hardware, a space test was scheduled for 2027, and then in 2025, they killed it. This is the story of nuclear thermal propulsion, the technology that could have revolutionized space exploration, why it got canceled, and whether we'll ever see it fly. But real quick, if you're into cutting-edge space technology and want to see more videos like this breaking down what's really happening in space exploration, hit that subscribe button right now. We're covering everything from revolutionary propulsion systems to the missions that actually make it to space. Trust me, you won't want to miss what's coming next. All right, let's get into it. The problem with getting to Mars isn't just distance. Mars is about 140 million miles away at its closest approach to Earth. Chemical rockets can reach it, but the journey takes 6 to 9 months. And those months in deep space are brutal on the human body. Every day you spend in space, you're bombarded by cosmic radiation and solar particles. On Earth, our atmosphere and magnetic field protect us. In deep space, nothing shields you. Studies show that radiation exposure during a Mars mission could increase cancer risk by up to 40%. Then there's the physical deterioration. In microgravity, your bones lose density at a rate of about 1 to 2% per month. Your muscles atrophy, your cardiovascular system weakens. By the time you reach Mars after 7 months, you're significantly weaker than when you left Earth, and that's when you need to start working on a hostile alien world. The psychological toll is equally severe. Confined spaces, isolation, communication delays of up to 22 minutes each way, and the knowledge that you're farther from home than any human has ever been. The longer the journey, the greater the risk of mental health issues. And let's not forget the practical problems. More time in space means more food, more water, more oxygen, more spare parts, more everything. The spacecraft gets bigger, heavier, more expensive. Launch windows become more constrained. And if something goes wrong, if there's an emergency, with chemical propulsion, there's no abort option. You're committed to the full round trip. So how do you solve this? You need a propulsion system that's far more efficient than chemical rockets. And for decades, scientists have known the answer: nuclear power. Nuclear thermal propulsion works on a surprisingly simple principle. Instead of burning chemical fuel like kerosene and liquid oxygen, you use a nuclear reactor to heat hydrogen gas to extreme temperatures around 2,500 degrees Celsius, and then expel it through a nozzle to create thrust. The key advantage is efficiency, measured in something called specific impulse. Chemical rockets have a specific impulse of about 450 seconds. Nuclear thermal propulsion can achieve 900 seconds or more, essentially doubling the efficiency. Same amount of fuel, twice the performance. What does that mean in practice? A Mars mission that would take 7 months with chemical propulsion could potentially be completed in just 45 days with nuclear thermal rockets. That's not a marginal improvement. That's a game changer. The concept isn't new. NASA tested nuclear rocket engines back in the 1960s and 70s under a program called NERVA, Nuclear Engine for Rocket Vehicle Application. They built and tested multiple engines on the ground between 1961 and 1973, achieving thrust levels comparable to chemical rockets with significantly better fuel efficiency. The technology worked. They proved it could be done. But NERVA got canceled in 1973 due to budget cuts and changing priorities. NASA was pivoting resources toward the Space Shuttle program, which promised more immediate visible returns. For decades after that, nuclear propulsion stayed on the shelf. Too expensive. Too politically sensitive. Chemical rockets were good enough for satellites and space stations in low Earth orbit. But as Mars ambitions grew in the 21st century, people started looking at nuclear propulsion again. In 2020, DARPA initiated a program called DRACO, Demonstration Rocket for Agile Cislunar Operations. The goal, develop and test a nuclear thermal propulsion system in space. In 2023, NASA joined DARPA as a partner, and Lockheed Martin was awarded a $499 million contract to build the experimental spacecraft. BWX Technologies would develop the nuclear reactor itself. The plan was to launch in 2027, conduct in-space tests, and prove that nuclear rockets were viable for future Mars missions. Everything seemed to be moving forward. Designs were finalized. Hardware was being built. By early 2025, contractors had completed high-temperature flow tests, built prototype pumps, and tested a nozzle through 20 start cycles at 2,700 Kelvin. And then it all fell apart. In January 2025, the mission's planned 2027 launch was placed on indefinite hold due to technical and regulatory challenges. Ground testing proved far more complex than expected. Safety requirements for handling nuclear material were underestimated. The timeline kept slipping. Then in May 2025, the federal budget for fiscal year 2026 proposed massive cuts to NASA's Space Technology Mission Directorate, specifically targeting advanced propulsion projects. By late June 2025, DARPA officially announced the termination of DRACO. So, what happened? Why kill a program that was so close to flying that could revolutionize Mars exploration? According to DARPA Deputy Director Rob McHenry, the decision came down to economics. When DRACO was conceived, launch costs were extremely high. But SpaceX's reusable rockets, particularly Falcon 9 and the upcoming Starship, drove launch costs down dramatically. The economics shifted. If you can launch propellant cheaply enough, you don't necessarily need the efficiency gains of nuclear propulsion. You can just carry more chemical fuel. As launch costs came down, the efficiency gain from nuclear thermal propulsion, relative to the massive R&D costs necessary to achieve that technology, started to look like less and less of a positive return on investment, McHenry explained. There were other factors too. Ground testing infrastructure proved to be a massive hurdle. Testing a nuclear reactor on Earth before flying it in space requires specialized facilities, containment systems, and regulatory approval. DARPA underestimated these challenges, and then there's the political dimension. Jared Isaacman, a private astronaut and businessman, publicly stated, "Nuclear thermal propulsion, I'm not a fan of. To test it, you're spewing radioactive debris here on Earth. It's not going to go over well with anyone." Public perception matters. Launching a nuclear reactor into space makes people nervous, even though the reactor wouldn't be activated until it reached orbit. And even though the Soviet Union successfully launched over 30 nuclear reactors into space between the 1960s and 1980s without major incidents, so DRACO is dead. But nuclear propulsion isn't completely abandoned. NASA is still funding research into nuclear electric propulsion, or NERVA, a different approach where a nuclear reactor generates electricity to power ion drives. Space Nukes, working with the University of Michigan's SPAR program, is developing nuclear electric systems that could theoretically reach Mars in about 45 days. The Ad Astra rocket company, founded by former NASA astronaut Franklin Chang Diaz, is developing the VAS-MR nuclear electric engine, capable of speeds up to 123,000 miles per hour. NASA has also awarded contract extensions to companies like Ultra-Safe Nuclear Technologies and General Atomics to continue research on reactor designs. The work isn't stopping entirely, it's just shifting away from the near-term demonstration mission. And L3 Harris Technologies is developing nuclear power solutions for both surface operations on the Moon and Mars, as well as deep space propulsion systems. The private sector is keeping the technology alive, even if government funding has dried up. But here's the frustrating part. We keep getting close and then walking away. NERVA in the 1970s reached technology readiness level 6, just one step away from in-space testing before it was canceled. DRACO got even closer with hardware already built before meeting the same fate. Why does this keep happening? Because nuclear propulsion is expensive, politically sensitive, and the payoff is years or decades away. It's easier to fund programs that deliver results faster, even if those results are less revolutionary. But as one DARPA official noted, there's been a strategic pivot toward nuclear electric propulsion. Nuclear electric is probably a more optimal long-term solution. Power in the space domain may be the critical enabler as much as the propulsion efficiency. So, what's the future? Will we ever see nuclear rockets fly to Mars? Maybe, but probably not in the 2030s like originally planned. The cancellation of DRACO means we've lost about a decade of progress. If and when nuclear propulsion gets revived, it'll likely be through smaller incremental steps rather than a big demonstration mission. In the meantime, NASA's human Mars missions in the 2030s will probably use enhanced chemical rockets with in-space refueling. Not as fast as nuclear, but more politically acceptable and easier to implement with current technology. The reality is this. Nuclear thermal propulsion could cut Mars travel time from 7 months to 6 weeks. It could reduce radiation exposure, enable abort scenarios, allow heavier payloads, and open up the entire outer solar system to human exploration. But we're not building it. Not because the technology doesn't work, it does. Not because it's impossible, we've already tested it successfully on the ground. We're not building it because of economics, politics, and short-term thinking. A 2021 National Academies report stated that developing nuclear thermal propulsion for Mars missions would require an aggressive program. But it was technically feasible by the end of the 2030s if sufficient funding and commitment were provided. The key word there is if. And right now, that if isn't looking good. Here's the bottom line. Nuclear propulsion isn't science fiction. It's real, proven technology that we've tested multiple times over the past 60 years. It could transform how we explore space, making Mars missions faster, safer, and more practical. But building it requires sustained investment, political will, and a willingness to deal with the complexities of nuclear technology. Those things are hard to come by when budgets are tight, and there are always more immediate priorities. DRACO's cancellation is a setback, but it's not the end. The technology will come back. Whether that's in 5 years or 20 years depends on whether we decide that getting to Mars quickly is worth the investment. So, will we see nuclear rockets to Mars in our lifetime? Maybe. The technology exists. The challenge isn't engineering, it's everything else. Politics, funding, regulation, public perception, those are the real obstacles. For now, chemical rockets remain the standard. Mars missions will take 7 months. Astronauts will endure higher radiation doses, longer confinement, greater physical deterioration, and we'll keep looking at nuclear propulsion and saying, maybe next time. The dream of reaching Mars in 45 days isn't dead. It's just on hold. Again,